is Gilles Pisier from Texas A&M University and Université Sorbonne. And the title of his talk today is From Injectivity to Approximation Properties for von Neumann Algebras. Please.
Thank you very much. It's a pleasure to be back in Istanbul, even though it's a little sad to commemorate the memory of von at the same time. But well, this is I guess not. We shouldn't be sad because I think he wouldn't want us to be sad. So let me start the talk. So it's a talk about injectivity and approximation properties, but I want to start by the motivation, which is a problem that is still open, a very big problem. I think I consider it a very big problem. And it's kind of a little bit forgotten. It's still open, and unfortunately, I can't report the solution. I will explain how I failed to solve the problem, or I will describe the approach that I took, and which doesn't quite do it. I also hope that perhaps people in the audience can sort of catch up and finish this. So the problem is very simple. The original problem that I'm interested in is just the problem of lifting when you have a C-star algebra and an ideal, and you look at the quotient C-star algebra. You take a separable Banach space X, and you have a contraction into the quotient, and you ask whether this admits a lifting. A contractive lifting, this is open, that's the best, but it's even open whether there always exists a bounded lifting. So this problem was studied in particular in the 1970s. I'll give a reference, and it was shown that the answer is yes, provided you have some approximation property by finite rank operators somewhere in the picture. It could be in the quotient C over I, could be in X, or the most general thing would be that the map T is approximable by finite rank contractions, okay, then the answer is yes, then you can do it. So if you have the approximation property, so AP will be always approximation property in short. M is for metric, so that's when we approximate by contractive maps. BAP will not appear actually, this is bounded approximation property. So the problem is open in general. It's known with these approximation assumptions, but it's open in general. There's a generalization that was developed, the theory of M ideals was developed after the 1970s by Efros and other authors. And in this setting, there exist counterexamples, but failing the approximation property related to that, but it's open in general. Okay, so the references, the old reference is Subshik, could say this covers the commutative case. It's a very famous paper on projections from little L infinity onto C0, very classical functional analysis, has something to do with the problem. And then the major references are Westerström, T.B. Anderson, and Ando in the early 70s. The other companion problem, which is less well known but also open, is the positive lifting problem. So same setting, exactly same setting, except X now has order structure. So let's say X is an operator system sitting in B of H. It contains the unit and stable by a joint, okay, self-adjoint, subspace unital. Is it true that positive maps lift to positive maps? And in the unital setting, it will more or less be automatic. It's the same question as asking whether unital positive admit unital positive liftings. Again, the answer is yes. This was proved by Westerström, and it's kind of Westerström and Anderson at the same time. I think Westerström really was a little bit before. Assuming the positive metric approximation property, this is true. So if you have positive finite rank maps that approximate the identity pointwise, let's say on X, then this is true. Could be, you could have the assumption on T, same setting. And then if you fix n, the same results hold for n positive maps. But what is known is that it is not true for completely positive maps. So completely positive maps, it's a whole subject of completely positive liftings on which there's an extensive literature. And so this is understood and it's related to nuclearity. Okay. So now let me move to injectivity. So I'll talk a lot about a variant of the notion of injectivity. It's wiser to just recall quickly the classical facts about injectivity. So phenomenon algebra is injective, as all of you know, if when represented in B of H as a phenomenon subalgebra, there is a projection from B of H to M of norm 1. And in fact, I always like to remember this problem on which I did some work many years ago, several decades ago, but it's still open whether just bounded projection implies that M is injective. But it's known that completely bounded projection suffices to imply that the algebra is injective. And another classical thing which is known due to Tomiyama is that if there is a projection of norm 1, automatically there is a positive one, in fact, a completely positive one. And it is, I mean, that same projection, sorry, is completely positive, and it is a conditional expectation. Now, after Cohn's very famous paper on injective factors, where he proved all sorts of equivalence to injectivity, in particular one that is called semi-discreteness, it became clear that the following fact is true. This is in this theorem, right? So it's hard to really attribute combination of Cohn, Shoyev-Ross, F-Ross-Lance. M is injective if and only if it has the weak star completely positive approximation property, which means that there exist normal maps, T alpha, of finite rank from M to M, and everything is weak star, and which approximate the identity weak star pointwise weak star. So T alpha X tends to X, weak star. Weak star is what operator algebraists sometimes call sigma weak. So it means the weak star topology of M has a dual space. Its phenomenon algebra is the dual of its pre-dual, so it has a weak star topology. Okay, so it's also equivalent to a matricial form of the weak star CPAP. And this matricial form is that there exists a net, same kind of net, but this time factorized through matrix algebras, M of a finite dimension N alpha, with U alpha, V alpha, all normal maps, and now unital completely positive. So UCP is the standard abbreviation for unital completely positive. Okay, I should point out that many people know this result in the C-star algebra setting. In the C-star algebra setting, it's very well known that a C-star algebra is nuclear if and only if it has the completely positive approximation property. So we have finite rank completely positive maps approximating the identity. And it's also well known that the bidual of a nuclear C-star algebra is injective, but these two facts that I just mentioned don't imply that the bidual of a nuclear C-star algebra satisfies this. It is a slightly stronger statement to have this weak star approximation property here, because it implies a norm approximation property in the dual. So if you're dealing with a nuclear C-star algebra, that theorem here tells you that the dual of the nuclear C-star algebra has the completely positive, the norm, completely positive approximation property. And well, this is not a consequence. Approximation properties don't pass to duals normally. Okay. So main example of non-injective, this is the end of the review, is the free group factor. So the phenomenon algebra of any free group of rank more than 1 is well known to be non-injective. And in fact, when you represent it in B of H, it's known, this is something that we proved with Hagerup in one of our 2 joint papers, this one is 1993. It is known that there is no bounded linear projection from B of H to L of F, okay? This is special to L of F. It uses Voiculescu's result that the fundamental group is, for the free group, is non-trivial. Okay, now I come to the notion of injectivity that this talk is about, which is a weaker notion and which is kind of, I don't know how to say, exotic or unorthodox. So it's a little bit unorthodox, and the results usually when I present them to experts, they are kind of, they think that there's something wrong. And in fact, I always think, I'm always worried whenever I go back to this subject here. So I call a phenomenon algebra seemingly injective if the identity of M factors through B of H, as indicated here with map U, map V, such that the identity of M is VU, and we just require that U and V are unital and positive, both unital and positive, and also, and it seems important, U is normal. So U is normal and they're both unital positive. So that makes them contractive. Unital positive implies contractive. So that means that U is isometric because this V is a contraction. So U is isometric, it's normal. And so by Sakai's theorem, we'll get that the image UM of U is a weak star closed subspace of B of H. Now, the big difference with the usual theory of injectivity is that here we are doing a linear isometric normal embedding. UM is a weak star closed subspace of B of H, not a subalgebra. Okay? Okay, so in this case, we have a projection. Of course, we have a projection onto this U of M, this subspace. There's a projection of norm 1, which is actually unital and positive just because the composition UV of the 2 maps give us the projection. So in fact, it comes out of the results that I will show later that we can always do a little bit better. We can always arrange, we change U, but keep the properties of U, but we can arrange that V is unital completely positive. So V can be the best type of maps, there's no problem, but U remains just unital positive. Okay, we can do that. That doesn't change the projection. The projection, you see, the projection is UV. So since U is bad, the projection is still bad. So another way to formulate what is going on here is that we're interested in algebras M that we call seemingly injective, which are such that we have a unital completely positive surjective map, an onto map from B of H onto M that has the property that it admits a unital positive and normal lifting. So that's the first connection with lifting problem. Okay, so once again, M is seemingly injective. If I can represent it as a quotient of B of H by a quotient map which is, realizes a metric surjection, but which is completely positive, unital completely positive, and liftable by a normal unital positive lifting. Okay. So suppose that we exclude the trivial case when M is nuclear. So the trivial case is like an algebra which is commutative, or which is commutative tensor a matrix algebra, or the direct sum of finitely many of those. That's the trivial case. And what I call the trivial case corresponds to just nuclearity for M, which is very rare because we are dealing with von Neumann algebras. So the the observation here stated in this proposition is that when M is seemingly injective and separable, separable pre-dual, then it is isomorphic as a Banach space with B of L2. So another, another thing which is a bit surprising if you compare it with what happens with injectivity. So this proposition holds because for trivial reasons, because it is well known that there is an argument due to Pełczyński, which is called the Pełczyński decomposition method in Banach space theory, and it says that when you have two Banach spaces and each one is complemented in the other, and also some extra condition, which here is satisfied by B of L2, because B of L2 is a nice enough space, then you conclude that actually there must be isomorphic. And so it applies here, and it tells us the result that M is isomorphic to B of L2, because what we just showed, what we have from the definition of seemingly injective is in particular that M will sit in B of L2, you get B of L2 by separability, with a contractive projection. So of course, B of L2 decomposes in the Banach sense as a direct sum of M and something. And on the other hand, M is a von Neumann algebra, and it's not nuclear, and it is well known. Well, it's a well-known classical result of Simon Wassermann, that in that case, M contains as a von Neumann subalgebra the direct sum of infinitely many copies of the matrix algebras with direct sum over all the sizes of the algebra. And this guy here, as a Banach space, is the same as B of L2. It is isomorphic to B of L2. Probably this result actually is also a consequence of Pełczyński's decomposition method. So this, which is embedded in M as a von Neumann subalgebra and which is injective, admits a completely contractive projection. And so definitely for any M except in the trivial case, we have this property here. So if our M is also complemented in B of L2, it has no choice, it's isomorphic to B of L2. So the point of this, which is a little bit surprising, is that precisely this applies to the von Neumann algebra, which was the bad guy for injectivity. The von Neumann algebra of any free group of rank more than one is seemingly injective, and therefore the von Neumann algebra that we get is isomorphic as a Banach space to B of L2. So we sort of are on a different, this is a different story from the injectivity, definitely. So what goes on is this. What goes on is that it's possible to characterize seemingly injective von Neumann algebras exactly as in the same way, in a parallel way that Con characterized injective using semi-discreteness, or what was called, weak star CPAP in the previous presentation. And so the theorem is that a von Neumann algebra is seemingly injective if and only if it has the same, the analogous property to what I just presented, with completely positive, but precisely you drop completely. So the identity is now a point, the definition, the definition of this property, matricial weak star PMAP, so P now for positive metric approximation property, is that there is a net of finite rank maps T alpha, normal, factorized in the form U alpha, V alpha, with all maps normal, unital positive, and it approximates the identity in the weak star sense. So the composition tends to the identity pointwise weak star. There's a variant where we drop matricial, and there it's a little bit less elegant. I have to introduce QWEP, and this QWEP, I will explain in a second what it means. It's short for quotient of a sister algebra with a weak expectation property. And so the equivalent form is that we assume that M is QWEP and it should have the weak star positive metric approximation property, which is the same as the previous one, except no mention of matricial factorization. So just finite rank positive maps, T alpha, unital positive, approximating the identity. Okay, so what is QWEP? So QWEP, I already said what was the meaning. WEP, weak expectation property. QWEP means that it's a quotient of a sister algebra with the weak expectation property. And one of the many theorems of Kirchberg in his famous paper in 1993 is that the phenomenon algebra is QWEP if and only if it's isometric as a Banach space, simply to a quotient of some B of H. That's enough. That's actually the simplest, in some sense, the simplest characterization of these QWEP. And then there are many more with more, more features. But that's kind of the simplest in that sense, quickest to say. It requires very little mathematics to explain. And in fact, what requires a little more is that actually you can adjust the quotient to be better, okay? So it's equivalent to be QWEP or to be isometric to a quotient of some B of H as a Banach space, quotient Banach space. But in fact, it's also equivalent to saying that there is a metric surjection from B of H to M, which is unital completely positive. So which is, the closest to a C-star representation. You can't get a C-star representation. They're not all quotient C-star algebras of B of H, but they are quotient by a unital completely positive maps of B of H. So what Kirchberg proved, one of the things that he proved at the end of his paper is that his conjecture he conjectured that all C-star algebras are like that. Couldn't find counterexamples. So what I call the Kirchberg conjecture is that all C-star algebras are QWEP. And it's equivalent to the Con embedding problem. That's precisely what he proves in this Invenciones 1993 paper. The Con embedding problem, as of course all of you know, asks whether in the original form, whether separable finite factors all embed in an ultra power of the hyperfinite factor R. So this is this R omega here, and it can be formulated in many other ways. And that's for finite phenomenon algebras. The advantage of the Kirchberg formulation is that it deals instantly with all C-star algebras, regardless of trace finiteness or not. And as all of you know also, and it's been mentioned already, there is a preprint, 205 pages long, that's been posted some time ago already, that contains a negative solution. But as far as I know, it hasn't been checked exactly by people I know. That might be a good point also to advertise my book. I wrote a book on what I call the Con Kirkberg Problem, which appeared at the beginning of the pandemic, in beginning of 2020. And that's Cambridge University Press, and you can find it. It's posted online without any problem. Just look on archive on any of my last 2 or 3 posting, and I reference the book and I reference the URL for the book, so you can download it. Okay, now positive metric approximation property means, of course, the obvious thing, and for a weak star closed subspace of B of H, it means that there is a net of weak star continuous maps that converge, that are finite rank and converge pointwise to the identity. Finite rank seems to be missing here. The main point in all the assertions that I made on the free group is that precisely in a paper by Hagerup and De Canière, which is sort of a complement of the famous paper of Hagerup on the approximation property, the metric approximation property for the reduced sister algebra of the free group. In this complement paper with De Canière, they prove that the Neumann algebra of any such free group has what I call the weak star unital positive metric approximation property. And the approximation property by the finite rank maps is obtained by a net of multiplier transformation. So actually a very good and even better than just plain approximation by finite rank. It's done by multipliers. There are not many groups that are, it's not well understood what this means exactly. There is a paper by Jolisin Valette that complements this, where they show that essentially property RD and an additional property naturally is a natural generalization of the case of free groups, but not much is known. And in particular, let's see. I don't think I have examples. Let me not say something silly, but I don't think I know of a group that fails this. Okay, so let me now show you how these things connect. One direction, which is really extremely easy, is that if the phenomenon algebra is QWEP and has the weak star positive metric approximation property, then it is seemingly injective. So this goes like this. I first use the Kirchberg result that if M is QWEP, we know that there exists a metric surjection from B of H to M, which is unital and completely positive. Okay. So we look at this W here in the diagram. The proof is essentially all it's going to be in the diagram. So we have this quotient map here, and then we assume that we have the weak star positive metric approximation property. So we have here this Ti, finite rank positive, to these subspaces EI, which are included in M. This inclusion lifts. This is part of Westerström result. Westerström showed that if we have the X with positive metric approximation property, we lift. So in particular, if it's finite dimensional, a finite dimensional operator system does lift with a positive map. So we have this Ri, which is a positive lifting, and that gives us a Ui by composition, which is the lift of in some sense, of Ti. So Ri Ti, this is Ui, that lifts our map. So now the diagram is, I just repeated the diagram here, and I repeated, of course, our assumption that the Ti's form an approximation of the identity. So we know that let's say we have an ultra filter of them, and the weak star limit of Tix is X. So we have a U is an ultra filter. Okay. So now we form the direct sum simply of copies of B of H. So that's denoted like this by operator algebra people. I can never get used to that notation because for me the product is the product. So that means that actually this is the unit ball is the product of the unit balls, and the algebra is the direct sum in the L infinity sense of these spaces Bi. So that's the Banach space notation for the same thing. So let's call this boldface B. Now M will be embedded into this boldface B by means of a normal map U, which is very simple, which is the direct sum of all these maps Ui that we built out of lifting of these finite ranks. Pi is just the ith coordinate. And W is, again, our quotient map from B of H to M. So WUI is TI, so this whole diagram does commute. And so we obtain a map V. We can define a map V from boldface B to M by just taking the weak star limit. Of course, weak star balls are weak star compact, so the weak star limit with respect to this ultrafilter exists, and so this defines a map that will still be unital and positive. So V is unital and positive. Actually, well, V is the composition, you see, of a unital completely positive and the coordinate. So in fact, V is even unital completely positive, and our U is, as announced, unital positive and normal. So that shows the claimed implication. Okay, so for the converse, the proof is a little bit more involved, but it turns out that fortunately the argument that works in the Con situation or in the Choi-Efros-Lance situation actually works without assuming completely positive, but just with positive. So now we're in the situation where we assume that M is seemingly injective, and we want to show that it has the weak star positive MAP or the weak star matricial positive MAP. Okay. So anyway, this implies QWEP because Kirchberg's theorem tells you that M is, isometric to a subspace of B of H with a projection of norm 1. So the theorem I quoted implies automatically M is QWEP. But the argument I'm showing will show the weak star positive MAP or the positive matricial MAP just the same. Okay, so this is just a sketch. I just want to write the key fact. The key fact here is this, which is a little less standard. It's not really difficult, but it's kind of not, perhaps something not stated anywhere. I'm not even sure, but it's sort of a variant of known things. The point is V here from B of H to M is only assumed unital positive. And then it follows that you have this property, which is a certain type of factorization for maps that appears all over, questions around Grothendieck, non-commutative Grothendieck inequality. So it's related to a certain application of Banach, but there is also some elements of the theory of self-polar forms which come up in this estimate. So anyway, that's I just wanted to say what is the key fact. The key fact is this one. We have this inequality. It becomes an equality when B is in the image of M. And once you have this, it's essentially possible to follow the Efros-Lance argument, which is the one actually that Con used. Con used a similar argument, and he mentions Efros-Lance in his paper. Although Efros-Lance's paper, which circulated as a preprint, this is a funny situation, has a date from later than all the other papers, but it had lots of ideas. It took 3 years to be published in advances. Oops. Okay, so that's just a sketch for the converse that seemingly injective implies weak star PMAP. Okay, a corollary of this, just for a little bit of emphasis, is that if we have a phenomenon subalgebra of another phenomenon algebra, so n subalgebra of M, and we know that there is a unital positive and hence contractive projection from M to N, then the weak star positive metric approximation property, let's say matricial. So the matricial weak star positive matrix approximation, the matricial weak star PMAP passes from M to N. And this is actually, I just want to emphasize, this is not a completely obvious fact, because the approximation property being in the weak star sense and the projection being often not normal. It is normal in the finite case, but there are lots of situations where the projection will not be normal. Nevertheless, this is true. And this phenomenon is parallel to the situation with Con's theorem, because when you consider exactly the same situation and you assume that M has the weak star CPAP, the completely bounded analog, then you conclude that N has the weak star CPAP, and this is this is not something formal. This requires the equivalence with injectivity. Because of course, if you pass to injectivity or to seemingly injective, then the assertion that the property is inherited by a subalgebra with a projection of norm 1 is obvious, because it's diagram chasing and it's completely formal. So a natural question, of course, is that has to be addressed is that, well, now maybe this class of algebras is just the class of algebras that are QWEP. And that, of course, would have been one way to sort out the subject. But the answer is no, but the answer is no by a rather, how to say, in a unsatisfactory way, certainly unsatisfactory for me, because this is no, because of a result which I know very well, which I have studied, 40 years ago when it came out, proved by Shankovsky, that the algebra B of H fails Grothendieck's approximation property, which was a major result, at the time, and also a result that is extremely complicated to prove. The proof is a paper in Acta Mathematica that's really it's very involved. But anyway, it's something we now know, and it implies that the bidual of B of H, of course, the bidual will fail the weak star approximation property. So there are, implications in the approximation properties from which this is clear, and so this is an algebra that will fail seemingly injective. The bidual of B of H, that's the bad guy. It's not really surprising, because this is in some sense a universal object for QWEP. It is QWEP, and it has the property that it contains any QWEP as a phenomenon subalgebra with a projection, a conditional expectation projection of norm 1. So it's sort of the universal QWEP. It's not too surprising that it sort of decides here the answer to this top question, but it's a sledgehammer. It's too complicated. It's a too complicated way to answer the question, and so obviously the questions that I'm asking after that are, to find more examples of QWEP phenomenon algebras failing the weak star positive metric approximation property. Since it's metric here, it should be easier to actually answer without using Shankovsky's theorem. So I have played with examples of groups with property T, which are a source of counterexamples to certain approximation properties of Hagerup, and I couldn't do it, but it seems that I suspect that a certain reinforcement of property T adapted to the passage from completely positive to positive, which is what I'm doing here, should be appropriate. I say, strengthening of property T, and I have in mind variations of the kind that, Vincent Laforgue did. Vincent Laforgue introduced a certain strengthening of property T, which I can't see how to relate to the problem here, but it's possible that another type of strengthening is relevant here. So just to fix ideas, I wrote here a conjecture that perhaps if we take the standard group with property T, which is SL3Z, and we take the product with the standard amenable ICC group, any one of them, you know, the phenomenon algebra, then by Con's result is the hyperfinite factor. And so the phenomenon algebra of this product G will be the phenomenon tensor product of the hyperfinite factor and the L of this gamma 2, which has property T. I suspect that this will not have the positive metric approximation property, and the arguments of De Canière-Haguet group clearly do not apply here, but I can't sort of gather this well enough in order to get a counterexample. Oh, I thought I would have been shorter. Oh no, I still have some time, I see.
Yes, you have 10 minutes.
Yes. Yes, and so I sort of jumped over the statement which maybe you read. So the inconvenient of B of H double star is that, of course, that's not a finite phenomenon algebra, but as most of you know, there is, you know, a procedure that comes from the Tomita-Takezaki theory that allows to reduce many questions about general phenomenon algebras just to the finite case. One passes from the finite case to the semi-finite case, and then by cross products argument from the semi-finite case to actually the type 3 case. This type of thing was used by Con in the injective setting, and it works here. So it works in the sense that you can easily show that if all finite phenomenon algebras are seemingly injective, then all algebras are seemingly injective. Okay, by following the path which I've just hinted at. And another way to say this is to say that, well, we can look at the ultra power of the hyperfinite factor, this R omega, okay? And this R omega, by definition of Con embedding problem, we know that it contains any finite, okay, separable pre-dual phenomenon algebra, which satisfies the Con embedding problem, which means the same as QWEP. So to say that any finite M is seemingly injective, in short, is the same as saying that the ultra power of R is seemingly injective. And so I conjecture that, well, I know that it is not, because it is a consequence of Shankovsky's theorem. That's what I'm saying. But I would really like to see a proof that it is not, where I can sort of, you know, see exactly the source of the obstruction to the approximation property. And I believe this is possible, but haven't been able to do that yet. Okay, and then I come to a problem, which is the connection with the source of the whole story. You remember that I started by telling you about this major lifting problem. So the difficulty that I have is that I couldn't quite do it, because seemingly injective turned out to work very well, but the problem, the lifting problem, apparently is related to a weaker notion, and the weaker notion, I needed a name. And so I didn't know what to call it. I'm still hesitant on the name. Weakly seemingly injective, that looks like too heavy, doesn't seem like a good idea. Okay, so yesterday I came up with remotely injective, and I hope you'll be indulgent, because that doesn't seem too bad. So M is remotely injective if it satisfies the same as seemingly injective, except that you drop positive. So you have a factorization of the identity through B of H with the map U, which is normal, contractive, and V can be a contractive. So V can be, let me see, is V, well, anyway, V is completely bounded and of norm 1. Probably it's also UCP. I just have a blank right now. But this implies that we have a contractive projection as usual, P, which is the composition UV from B of H to UM. This UM is isometric to M, and it's weak star closed. It's a weak star closed copy of M in B of H. But in this case, I don't have the theorem that this implies an approximation property. I don't know that this implies an approximation property, and so I have no counterexample. So what I'm asking now is more extreme. It's an embarrassment. Is it true that every von Neumann algebra, which is QWEP, so you see that QWEP must be there because by Kirchberg's theorem, we are dealing with an algebra which is, a quotient isometric to a quotient of B of H. So it's QWEP. Is it true that all QWEP are like this, are remotely injective? So this is the embarrassing problem. I see on my screen, I happen to see my friend Bernie, who is there, and it reminds me that would be a good idea to mention that there is a whole literature on the range of contractive projections on C-star algebras, range of contractive projections on von Neumann algebra, or on B of H, range of contractive projections on B of H. There's an early paper by Efros and Sturmer on the case of positive unital projections. And then there's a characterization by Rousseau and Friedman on the range of contractive projections on B of H. And of course, I looked at all these papers, and surprisingly, as far as I've seen so far, it gives information on this range UM, which somehow I don't seem to be able to use. It seems that in the situation that I'm looking at, anyway, my UM is a copy of M, and this information that comes from these results doesn't seem to click, but here I might be missing something. Okay, so the problem in the end is, does remotely injective imply some approximation property? So then if it does, at least I can use Shankovsky's theorem and conclude something. But I definitely conjecture that there exists a QWEP which is not remotely injective. More explicitly, it should be, again, the ultra power of the hyperfinite factor, or an ultra product of matrix algebras over all dimensions n, or the bidual of B of H. And the reason that I ask this is that if the answer is positive to this conjecture, then I can solve the contractive lifting problem. Because I have the theorem, which is, if you like, a conditional theorem, which is not really difficult, by the way, but it's sort of in the same style as the previous results. And it says that if we have a QWEP von Neumann algebra M, like is written here, quotient of B of H, and if all separable subspaces X have the contractive lifting, so X separable subspace, and we assume it lifts, then M is remotely injective. So it seems that here this lifting problem will force some approximation property. That's my hope, but I could be wrong because I spent a lot of time already on it. So my hope is that this will force an approximation property, and then we can therefore derive a counterexample to this contractive lifting problem. Thank you very much. This is the end of the talk.
Thank you for this interesting seminar. And are there any questions?
Yeah.
Yes.
This might be a naive. Can you hear me?
Yes,
yeah.
yes, please.
Okay. This might be a naive question, but is there a connection between this seeming injectivity and exactness for C-star algebras?
I thought of connecting, yes, with weak star, Ozawa. By the way, I forgot to say that Ozawa has studied operator versions of lifting property, and this is very influential in all the results that I've presented. His results on operator lifting property have something to do with all the things that I'm discussing. But he also has a paper on weak star exactness, and I couldn't relate to weak star exactness, but I thought of that. Yeah, so it might be that yeah.
Well,
this positive approximation, weak star positive approximation property should imply some form of weak star exactness, but couldn't do it.
Yeah, I mean, this could give an explanation as to why the free group factors are almost injective, or seemingly injective, I mean, because that's done from the regular representation. So it goes through the reduced C-star algebra, which is exact. It would be nice to have some kind of connection that might be able to characterize exact C-star algebras, like we have the characterization of nuclear C-star algebras, that the second dual is injective. You know, I wonder if it could be possible that a C-star algebra is exact if and only if its second dual is seemingly injective, something like this. Because the exact C-star algebras are sort of the next class of C-star algebras beyond the nuclear ones. You know, it would be nice to have a characterization in terms of the von Neumann algebras they generate in representations.
Yeah, well, the seemingly injective doesn't pass to subalgebras, only, you know, in the usual thing, only in the finite case. So while exact, you know, passes to subalgebra. So you'll need to formulate something with a projection maybe, but something might be true. That the bidual of exact, yes, might be, well, what can be true? Bidual of exact can't be, that can't be right? Because because all the subalgebras are exact. So that I'm not sure.
Yeah, there may not be any kind of bidual characterization of exactness, but I've wondered about this over the years, whether you could get something like this.
Thank you.
Other questions? If there are not other questions, I have a little questions, but so summing up, if we want to characterize these different levels of injectivity through the properties of the projection, is that if we have an injective projection, then the definition gives us a conditional expectation. And so remotely injective, maybe you just told that it's contractive projection, and when you have a seemingly injective, which is the best projection that we can have? Or
the unital positive.
Unital positive, okay, thank you.
Yeah, the thing is that the difference, you know, at first glance, the difference between remotely injective and seemingly injective seems very slight from, you know, usual experience of operator algebras. The things are contractive. All you need to do is, you know, fix the unit, then you will get positivity for free. You know, that's a very usual type of argument. I couldn't make it work there, so it's extremely irritating, frustrating.
So if there are no other questions, we can close this session, and I thank again all the speakers for these wonderful seminars and for accepting these invitations, and we can resume at 8:30 Istanbul time.